Hey everybody, happy Monday. This is happy February. We're discussing section 6.6 today, which is super hard. It's called improper integrals. I mean, pretty much everything we do is hard in this class. But some of the stuff that we've done that's really hard, you probably never will end up needing to do. You probably won't do integration by parts. You probably won't do trig substitutions. When there are all these computer tools in your life that will do integrals for you, you probably won't be doing integrals by hand. But it's good to understand why they work. But the stuff that we're doing today, improper integrals, you do encounter all the time. I mean, if you're in the sciences, you encounter this stuff. And so it's good. It's going to be very important that you really understand why this stuff works. All right, so what I want to start with is, oops, there's a hole in my pocket and I feel things creeping down my legs. All right, I want to start with a review of graphs of the form 1 over x to the p. Y equals 1 over x to the p. And so I want to just do a couple of sample x values. And this is for x greater than 0. So I'm going to do just a few representative x values. So say x equals 1/4, x equals 1, and x equals 4. And the first graph that I want to do is y equals 1 over x to the 1/2. So in other words, 1 over square root of x. So when x is 1, y is equal to 1. When x is equal to 4, y is going to be 1 over square root of 4, so 1 over 2. But when x is 1/4, y is going to be 1 over the square root of 1/4. So 1 over 1/2. So in other words, y is going to be the number 2. Okay, the next one I want to consider, the next graph is y equals 1 over x to the 1. In other words, just 1 over x. Well, the y values on this graph are easy. 1 over 1 is 1, 1 over 4 is 1/4, 1 over 1/4 is the number 4. Easy peasy. Now let's go over to our final graph, which is going to be y equals 1 over x squared. Well, when x is 1, y is going to be 1 again. When x is 4, y is going to be 1 over 16. And when y is 1/4, when x is 1/4, y is going to be 16. Now I'm going to do a little bait and switch. I just chose 3 particular values of p. But I'm going to change now to families of graphs. So we're considering x greater than 0. So there's my x, here's my y, and the graph of y equals 1 over x, we already know, I'm going to actually draw that one, and it's got these 3 points on it. So it goes through 1, 1. It goes through 4, 1/4. And it goes through 1/4, 4. and it looks like this. So this is y equals 1 over x. So that's p equals 1. Now let's draw the green graph. Notice the y values on the green graph are not as high over here. So this graph goes through 1/4, comma 2. But the y values are greater over here. It goes through 4, comma 1/2. So the green graph is above the red graph over here. Crosses through that point with it, and then it goes below it. Now let's think about the blue. Oh, so I'm sorry. I shouldn't have done that. I shouldn't have given you the coordinates. I just want to talk about the green graph is y equals 1 over x to the p, where p is any number between 0 and 1, including this green one that we just did. So it doesn't matter what my value of p is. We did p equals 1/2, but we could have done p equals 1/3, p equals 1/4, whatever. The graph is going to look like that. And then the third family that I want to consider is the blue family. Now the blue family, here's a representative of it. Here it's 1 over x to the p, where p is greater than 1. Y equals 1 over x to the p, where 1 is less than p. So p is greater than 1. I like writing less than signs, not greater than signs, so I always write that. And so the green graph is the graph for p between 0 and 1. The red graph is for p equaling 1, and the blue graph is for p being greater than 1. All right, so that's the review. We're going to leave these graphs here because we're going to be referring to them for the rest of the hour. So that's part 1, review of those. Okay, part 2 is going to be integrating this. So taking one of those graphs and doing this integral. Now I'm not saying which graph yet, but it's going to look like this. All those graphs go through 1, 1, and they all go up. Anybody notice anything weird about that? The idea of doing that? Yeah.
Little sliver, but x equals 0, it will go up forever.
Right. There's no y value on the graph at x equals 0. So we've never had an integral like that. In Calc 1 and in this class so far, when we do integrals, we do functions that don't do this. So the problem with this idea is that the graph is discontinuous at one of the endpoints. Or it doesn't matter that it's at the endpoint. The thing is, there's a place in the interval from 0 to 1 where the graph is discontinuous. So this is an improper integral in its type 2. And what's type 2 about it is that the integrand is discontinuous somewhere in the interval. So how do we do this? Well, we define this integral from 0 to 1 of 1 over x to the p to be this. We don't integrate from 0 to 1. We integrate from a to 1 of 1 over x to the p. And then we take the limit as a gets closer and closer, as a goes to 0. So the limit as a goes to 0 from the right. We only consider positive a values. So the idea is that we look at this interval now that's an honest interval. And so that integral is an honest integral. And then we see, what's the number? This is going to be a number. And we see what happens to the number that's that area if I pull this a value closer and closer to 0. So this integral, we say, is equal to this if this number, if this limit exists and is a real number. Now here I have to say, I usually feel like this book does things perfectly or close to perfectly, but they're really weird about this stuff. Way back in chapter 1 or chapter 2, we learned about limits. Like chapter 1 in Calc 1. And we had limits that either the limit was a number or the limit did not exist. And then shortly after that, we changed our definition of limit. We said, okay, we can have limits that are real numbers. We can also have limits that are infinity or minus infinity, or limits that are neither of those and don't exist at all. And so the books are very cheesy about this. If the limit is infinity, do you say the limit exists or not? Well, again, the book can be ambiguous about this. I want to say the limit exists. We've just expanded our definition of what we mean by a limit existing. It doesn't exist as a real number, but it exists. It's the infinity symbol. Well, our book in this section they don't make any kind of distinctions. They say if this limit exists and is a real number, then that's what we say this integral means. But what's really frustrating is that in WebAssign they have a different approach than what's in the book. So we say the integral converges, and in this case, and its value is that real number. Now, what if the limit, so if the limit is not a real number, then we say that the integral is divergent. And that's as far as the book goes. They just say if the limit does not exist as a real number, then you say the integral is divergent. But the thing is, in WebAssign, you're actually asked to give a value anyway. And so sometimes you actually have to enter a value that's the infinity symbol. And that's not talked about in the book. Or it's not talked about that way. So let me do an example. Let's do this integral from 0 to 1 of 1 over x dx. So this is the case where p is the number 1. It's that red graph over there. So we're looking at a region that looks like this. So this is the limit as a goes to 0 from the right of the integral from a to 1 of 1 over x. Okay, what's the integral of 1 over x? Marcy?
Natural log of x.
Okay, somebody else. Improve that.
Natural log of the absolute value.
Good. So I have the limit. So almost, Martha, but you got to remember the absolute value. So limit as a goes to 0 from the right, and I have ln of absolute value of x, and then I have to evaluate that from a to 1. Now, having written that, can we simplify that? What kind of x's are we talking about here?
X's that are very close to 0.
And in general, are the x's that we're talking about positive things or negative things? Yeah, so raise your hand, always. So we're talking about positive x's. So x is greater than 0, all of them, whether they're close to 0 or not. We're talking about positive x's. So we can simplify this as the limit as a goes to 0 from the right of ln of x. We don't need to keep dragging around the absolute value symbols. Okay, so then how does that look? So the limit as a goes to 0 from the right, we have ln of 1 minus ln of a. Okay, so somebody raise your hand. How can I simplify that expression? What's ln of 1?
0.
Good. So this is limit as a goes to 0 from the right of minus ln of a. So what is that limit? All right, so it's Monday, so that means you have to once again remind yourself of what the logarithm graph looks like. Every damn Monday of your life, you got to do this. So let's remind ourselves. And how do we get there? Here's the graph of y equals e to the x. It goes through 0, 1. It goes through 1 comma e. And it has an asymptote on the left that's y equals 0. So the graph of y equals ln of x is the inverse function for this. And it goes through 1 comma 0. It goes through e comma 1. And it has a vertical asymptote that's got a line equation x equals 0. Okay, so on this graph, when my x is very close to 0, but to the right is 0, how would you describe the y values? Chase? Say it again?
Negative infinity.
Well, no, the x values are close to 0, but they are numbers. So how would you describe those numbers? So x close to 0, but positive. So 1 over x is huge and positive. So the numbers they're definitely numbers. So I'm sorry, A is a number that's close to 0 and positive. And so 1 over a is a huge positive number. I'm sorry. Say what you said again.
I thought you were talking about the y as a negative infinity.
Yeah, so ln of a, I don't want to say negative infinity. ln of a is a number. It's huge and negative. So this thing, ln of a is a huge negative number. So minus ln of a is a huge positive number. So it's not infinity. Infinity is not a number. What we're looking at here is a huge positive number. So minus ln of a is huge and positive. So what we're looking at here is that white area that's not a bad one. It's the one that goes from A to 1. And its value is minus ln of A, which is a huge positive number. Now, so again, that's not infinity. That is a huge positive number. But when I do this and I park in front of it the limit symbol, then I get infinity. So the limit is infinity. So what's in here is a huge positive number. The closer A gets to 0, the bigger and huge and positive that thing gets, so the limit is infinity. So again, back to chapter 1. In the early days of chapter 1, we would have said, oh, this limit doesn't exist. And then later on, we came back and we said, well, okay, we're going to say this limit equals infinity. But the idea here is the limit, so the integral from 0 to 1 of 1 over x dx is divergent. So in WebAssign, you're asked to say whether the integral is convergent or divergent. It's definitely divergent. But then you're asked to give a value. And this is, again, what's weird. The book doesn't present these questions that way. Its value is, well, in that box in WebAssign, you'd enter the infinity symbol. It's not a real number, but that means that the limit is, we say the limit is infinity. All right. Now, look at this graph over here. We're working from 0 to 1 on this graph. And we found that the area under that red graph is, well, it's not a real number. Well, we say it's infinity. So if we're looking at, from 0 to 1, what do you think the area under the blue graph would be? I see one hand up. Get some more hands up. If the area under the red graph is infinity, yeah. Yeah, because the blue graph is above the red graph. That's the essence of what the book calls the comparison theorem. If you have two graphs, and one of them is always above the other, and the one on bottom has infinite area, then the one on top does as well. So by the comparison theorem, we can say for sure that the integral from 0 to 1 of 1 over x to the p for the blue graph is also going to be infinity. So what's going to be interesting, though, is going to be what happens with the green graph. Well, I don't know. The comparison theorem doesn't work there. I mean, the red graph has infinite area over here, but the green graph is lower than that. So we have to investigate that. So example 2. Is to find the integral from 0 to 1 of 1 over x to the p dx in the green case, when p is a number between 0 and 1. So let's call this the signed area. And so that's going to be the limit as a goes to 0 from the right of the integral from a to 1 of 1 over x to the p. Now, for the purpose of integrating, we want to turn this into, so it looks like a power function. So this is going to be the limit as a goes to 0 from the right of the integral from a to 1 of x to the minus p. All right, so we have a power function. So somebody tell me, what is the antiderivative of x to the minus p? give you a hint. The rule starts with p and rhymes with our rule. What's an antiderivative of x to the minus p? The power rule for antiderivatives. How about the power rule for derivatives? What's the derivative of x to the minus p? Trent?
Minus p times x to the minus p minus 1.
Right, so that would be the derivative of x to the minus p. So what's the general antiderivative of x to the minus p? Trent?
X to the negative p plus 1.
Right, x to the minus p plus 1 over minus p plus 1. And I have to evaluate that from a to 1. And I have a limit in front of this whole thing. So the limit as a goes to 0 from the right of, well, let's see, I'm going to have 1 to the minus p plus 1 divided by minus p plus 1. And then I'm going to have minus a to the minus p plus 1 over minus p plus 1. All right, so p is a number between 0 and 1. We have to figure this out. There's no way to dress this up. This is hard. So 0 is less than p, which is less than 1. So what about I have a number that's between 0 and 1, and I'm going to take 1 minus that number. So what's my result going to be? Like, for instance, yeah?
It's going to be between negative that number and positive that number?
Not quite. Think about like the number 3/4. That's between 0 and 1. What's 1 minus 3/4? 1/4. That's still between 0 and 1. How about 0.99? That's between 0 and 1. 1 minus 0.99 is 0.01. That's also between 0 and 1. So 1 minus p is also going to be between 0 and 1. So it's a positive number. So this is, this is the same as saying 1 minus p. So I have a raised to a positive power. So a is a number, it's a positive number, and I raise it to a positive power, so I get a positive number. So what is this going to be? What's that limit going to be? Trent's hand's up. Anybody else? You have a number that's a positive number, a, and it's being raised to a positive power, and then I make my a get closer and closer to 0. Exactly. So this limit is going to be the number 0. Again, I can't dress this up. It's hard to puzzle through this stuff. So the limit of this part of it, this numerator is going to 0. The denominator is just chilling. It's just some number. So I've got a numerator, it's getting closer and closer to 0, divided by some number. So this thing is going to 0. So this limit is, and notice, what's 1 raised to the minus p plus 1 power? 1, yeah. Who's the smartest person on Star Trek, the old Star Trek? Spock, the smart one, right? So find the find the Star Trek episode where they're looking at some big-ass thing on the screen, and Captain Kirk says, "What is that, Spock?" And Spock says, "Well, I don't know, but I would estimate that its size is 1 to the 40th kilometers," which is pretty funny, because apparently none of the writers realize that 1 to the 40th is just the number 1. So 1 to the minus p plus 1 is just the number 1. So this ends up being 1 over minus p plus 1. So in other words, 1 over 1 minus p. Wow. Go back to this. That shaded area is a number. So for example, the integral from 0 to 1 of 1 over square root of x, that would be the integral from 0 to 1 of 1 over x to the 1/2. According to that formula, it would be 1 over 1 minus 1/2. So 1 over 1/2, it would just be the number 2. So in our picture, I'd have a green graph. I'm going to go back to just the generic one. So here's the graph of y equals 1 over x to the p, where p is some number between 0 and 1. And this area, signed area, is 1 over 1 minus p. That's really cool. The graph shoots up to infinity there, but the area is a number. All right, so let me summarize. Actually, I'm going to put this over here. I'm going to move over here. So here's a summary about the integral from 0 to 1 of 1 over x to the p dx. So the values of p, we've been dealing with that. So we have the green case, 0 is less than p, less than 1. We have the red case, which is just 1 over x, so p equals 1. And then we have the blue case, which is p greater than 1, or I like to say 1 is less than p. And so the question is the integral from 0 to 1 of 1 over x to the p convergent or divergent? Well, we found that in the green case, it was convergent. And its value is 1 over 1 minus p, which is a number. In the case of the red graph, remember that we found that it was divergent, because the integral was not the value of the integral was not a real number. But if this was WebAssign, you'd have to say, okay, the integral is divergent, but then you'd have to go on and give its value, and the value was infinity. Now remember, we didn't do the blue case. We just looked at that graph over there and realized, oh, the graph of the blue graph is above the graph of the red graph. So the blue graph is divergent as well. And so it's infinity. Its value is infinity. So again, I can't dress this up. This is just hard. part three, is we're going to consider integrals from 1 to infinity of 1 over x to the p dx. You don't really speak the dx, you just say the integral of 1 over x to the p. So think about this. When x is a number greater than 1, 1 over x to the p is a number. There's nothing wrong with the y values. But what's improper about this integral is that the interval itself is an infinite interval. So this is improper of type 2, which is an infinite interval. So we're talking about this kind of thing. These graphs all go through 1, 1, and they all do this. And we're talking about this shaded area. What is this? Well, the book presents this as we define this symbol, the integral from 1 to infinity of 1 over x to the p, to be this. We just integrate from 1 to b. So we look at this picture. We go from 1 to x equals b. And we only go that far. The graph goes on, but we just think about this area. And we look, what do we get for that? And then park the limit as b goes to infinity. And again, if this limit exists and is a number, then we say that the integral converges and its value is that number. If the integral, if this limit is not a real number, we say that the integral is divergent. But we can still talk about its value. All right, now, I'm not going to go through these details because they're in the book. The book presents this case. They start chapter 6.6 by talking about this kind of integral, and they go through all the stuff that I just went through a while ago. It's hard figuring out these terms, what's the limit of these terms. So see the book. But I'm going to present the results. So value of p, and then is the integral from 1 to infinity of 1 over x to the p, is it convergent or divergent? And then finally, what's its value? All right, so remember, over here on this picture, we're now looking at these same three graphs, but we're looking at the right side of this picture, from this point to the right. Well, it turns out, the first example the book does is when p equals 1. So we're looking at the integral of 1 over x. And we find that in this case, the integral is divergent. So, and its value is infinity. That's that red graph. So looking at that picture, if that integral is divergent, what do you think, what can you say about one of these? Either p between 0 and 1 or p greater than 1. Knowing that this is divergent, we can right away say something about one or the other of these. Which one? Liam? Ian? Yeah, Ian?
The green one?
What about it?
Divergent.
Yeah, exactly. Because see, in that picture over here, the green graph over on the right is above the red graph. So if the red graph encloses an infinite area, then the green graph does as well. So we don't even have to do the details, but they do in the book. But because in the book, the comparison theorem comes later. So this is divergent. And so its area, its value would be infinite. And it turns out that when p is greater than 1, the integral is convergent. So again, even though this tail goes on forever, the area that it encloses is finite, and it's 1 over p minus 1, not 1 minus p. That's good, because notice, remember, p is a number greater than 1. You subtract 1, you get a number that's greater than 0, so this is going to be a positive area. And it's funny to think about what does it mean that this tail goes on forever. It's funny, I always I try to think about area in terms of paint. It's the amount of paint you would need to paint the whole thing. But if you're a painter, you're never going to finish because it goes on forever, right? So I don't want to, I'm going to go crazy here thinking about that. So let's think about this. Your job is to paint this whole thing. Of course, you're never going to finish because it goes on forever, but you have to go to the paint store and you want to buy paint. You want to make sure that you're never going to run out. Well, if you buy any less paint than this, at some point you will run out. Even though the graph goes on forever, your paint will run out. If you buy this blue paint, buy this amount of paint, you will never run out. It's the least paint you could buy, and know that you could start on this endless task of painting this and you would never run out. All right. So that was part 3, integrating 1 over x to the p from 1 to infinity. So again, that's presented in the book, and it's hard, and I can't dress that up. Alexandra, did Cassidy ever? Okay. Part 4, or example 3, integrating this. Integral of x e to the minus x squared. So remember from Calc 1, if you had me for Calc 1, you got tired of me talking about this famous graph. This is the graph of y equals e to the minus x squared. It's a bell-shaped curve. There's a whole family of these things. The key is that it's an exponential function with a quadratic polynomial in the numerator, in the exponent, with a negative leading coefficient. But that's not our graph. Our graph has an x in front of it. Well, clearly when x is equal to 0, I'm going to take the y value in that graph and multiply it by 0, and I'm going to get 0. So this graph goes through 0, 0. And then to the right of 0, well, I'm going to be taking those y values and multiplying them by some positive number. So it turns out that this graph looks like this. Sorry about that. So on the left side, the graph looks like this. So we're talking about this shaded area. Well, this is improper, again, because it's an infinite integral, but it's doubly infinite. So we have to define how to deal with this. The way we deal with this is we break it up. We go from minus infinity to 0, plus we integrate from 0 to infinity, x e to the minus x squared. So let's call this integral A, and let's call this integral B. Let's work on B. The integral from 0 to infinity of x e to the minus x squared. So, as you know, as I've said before, we do this as a limit. The limit as b goes to infinity of the integral from 0 to b of x e to the minus x squared. So remember, the fundamental theorem of calculus says that the way that we do this integral is we do the indefinite integral, and then we evaluate from 0 to b. And so that's going to equal the limit as b goes to infinity of something minus something. Now off to the side, this is how I always did it in Calc 1, I'm going to do the indefinite integral details. So we have the integral of x e to the minus x squared dx. So I'm going to do a substitution. My inner function, so it's minus x squared, that's going to be my u. So that's going to give me a new version of that, the inner function. And then I always did this the same way in Calc 1. I would get a new version of the dx. Well, the dx, remember, is 1 over u prime du. Well, u is minus x squared, so u prime is minus 2x. So minus 1 over 2x du. So there's my red substitution. So then I substitute those parts in. I don't do anything with that x for now. I have x e to the minus u times minus 1 over 2x du. So I made my red substitution there, and I made my green substitution here. Or this should just say e to the u, sorry. And then I cancel. Notice that my x's cancel, and I get, and the minus 1/2 comes out. The integral of e to the u. What's an antiderivative of e to the u? Marcy?
Is it e to the u plus 1 over e plus 1?
Somebody else.
E to the u?
Just e to the u. Yeah. Marcy, you made the common mistake of thinking of this as the power function, but it's an exponential function. So it's minus 1/2 e to the u plus c. But now I got to substitute back. So minus 1/2 e to the minus x squared plus c. So that's what goes in. That's all the indefinite integral rule, indefinite integral details. So that goes here. Minus 1/2 e to the minus b squared and then minus 1/2 e to the 0 squared. Okay, so e to the 0, that's just the number 1. So this whole thing is just 1/2. Now look at this. E to the minus b squared, when b is getting more and more positive. So let's see. E to the minus b squared is the same as 1 over e to the b squared. B is huge and positive, so b squared is huge and positive. So e to the b squared is huge and positive. I'm sorry, minus b squared is huge and negative. I'm sorry, that's okay. E to the b squared is huge and positive. So 1 over e to the b squared is very close to 0. So this term here goes to 0. So that white area on the right side has value 1/2. What do you think is going to be the value of A? Sam, you raised your hand, kind of. If the value of this integral is 1/2, what do you guess is going to be the value of this one? Yeah, so it turns out that the integral A is 1/2, or minus 1/2. So the integral from minus infinity to infinity of x e to the minus x squared is going to be minus 1/2 plus 1/2, so it's going to be the number 0. So the integral converges and its value is 0. Marcy, do you have a question?
No.
Okay. Now you have to be careful about these integrals. It's subtle. You might think, why don't I, instead of breaking this up into 2 integrals, why don't I go from minus b to b and just do that? But that's not the way it's done. And so, for instance, this is cool. I have half a minute left. Or I have 2 minutes left. What about this? The integral from minus infinity to infinity of x cubed. Trent? Well, turns out it's divergent. You can't actually give a value. So this is an infinite area. This is an infinite area. And so the official party line is the integral is divergent. And you cannot say infinity minus infinity equals 0. You cannot say that this area is 0. It's a very subtle thing which the book pretends you won't notice, but now I've put it in your head, so you're going to have to have sleepless nights along with me. You can't do arithmetic with infinity. You cannot say that infinity minus infinity is equal to 0. So you can't say that. So this is divergent. But again, we've had divergent integrals where we could say the integral has a value that's infinite. But this is divergent and undefined value. Because again, the way you'd have to do this, you'd have to integrate the right side, you'd have to integrate the left side, and then you'd have to add them. And you can't do arithmetic like that with infinity. All right, thanks everybody. So again, this stuff is hard. You've got a hard week of work ahead of you. Thanks, Gabriel.